my operating systems project, an energy-aware CPU scheduler. The goal of this project is to simulate multi-core CPU scheduling while also optimizing energy consumption using DVFS, which is dynamic voltage and frequency scaling. Let me walk you through the system. In the step one, which is process input, here we define the processes. Each process has a process ID, process arrival, which is time when the process enters the ready queue, burst time, which is CPU time required to complete the process, and deadline, which is the latest time by which the process must complete. This allows us to simulate both normal scheduling and real-time scenarios. From here, we can add the or delete and process. Next step is simulation setup. In this section, we configure how the CPU behaves. We choose the number of cores, algorithms, which has energy aware, ETS, EDF, round robin, SJF, and FCFS. FCFS is which executes in arrival order. SJF selects the shortest job first for better efficiency. Round robin uses time slicing to ensure fairness, and EDF prioritize tasks with the earliest deadlines and useful in real-time systems. And energy aware task scheduler algorithm. This is a core algorithm in our system, which is energy aware task scheduler, which balances performance and power consumption. It is the main focus because it considers both execution, efficiency, and energy uses. And next we have DFS mode, which is a key part of this project. This adjusts CPU frequency to control energy consumption. In this, we have power saver, which decreases the frequency to save energy, but it is slower, and balanced and performance. These are the three modes. Let me select the balanced one, and then after configuring the settings, we click the run simulation button, and now it's computing the. Now we got the results, and in this result section, we can see the simulation score, which is 877, CPU utilization, average turnaround, deadline success, and number of processes which missed the deadlines, and the command score, which is the overall score of the scheduling algorithm, CPU load, queue flow, turnaround, live mode, core meshes, number of cores used, and then in this inside section, we can see the efficiency of the scheduling algorithms. Here we have CPU usage, waiting pressure, turnaround tempo, energy efficiency, and the CPU algorithm which is used, total time taken, total energy consumed, DFS, using DFS, how much percent of the energy has been saved. And in the last section, this is one of the most important and unique part of this project, which is now which gives us the insights of the number of deadline misses and why the deadlines have been missed. For example, P3 is missed, P3 missed at 14, finished at 15.6. Queue congestion delayed the first dispatch by 7.4 time units. And next we have bottlenecks. Bottlenecks identifies congestion points in the system. For example, three processes were waiting around T6, which indicates a queue bottleneck. And next, in this suggestion tab, the system intelligently suggests improvements. For example, increasing number of cores, switch to EDF for better deadline handling, or use round robin to reduce long waiting times.
Now my part is Gantt chart, so I am looking on my Gantt chart part. So in my Gantt chart, core 1 handled P1 process 1, process 5, and process 3, one after another, while core 2 handled process 2 and process 4. The interesting thing here is the color and frequency difference. P1 and P2 run at 0.8 GHz because they had enough time. Shulk while process 3, process 4, and process 5 had to run at 2.0 gigahertz to try to meet their deadlines. Now I'm coming on P processors. So in P processes, P1 and P2 processes successfully meet their deadlines with the zero waiting time, and they actually saved energy compressed to the baseline minus 8.64 and minus 5.76 units. That's DVFS doing its job perfectly, but process 3, process 4, and process 5 are missed their deadlines. Process 4 is the biggest reason. It had a burst time of 14 but a deadline of 10 only, which has nearly impossible. Process 3 waited 10.4 times unit before even getting CPU accesses. Way too late. The delta baseline column shows the energy saving. P1 process 1 and process 2 showing negative values, meaning they saved energy. Process 3 and process 4 on process 5 show 0. They run at fully speed and still cannot make it. So scheduler did well on energy efficiency, but deadline management for heavy processes is the clear area for improvement. Thank you for watching.
Now let's move to the chart section. This section presents the visual analysis of the simulation, helping us compare performance and energy efficiency across different scheduling algorithms. So starting with the energy versus time chart, this shows uh, this shows how energy consumption increases as execution progresses. The cumulative energy curves rises set steadily. Each segment represents energy used during different execution intervals. This helps us understand how longer execution or higher frequency directly increases total energy consumption. So at different time intervals, we can see the cumulative energy and different at cumulative energy consumed at different intervals. So next, moving to the average waiting time graph, we compare average waiting time across algorithms, FCFS, SJF, round robin, and different algorithms we have in this project. FCFS, SGF, round robin show lower waiting times, and EDF and EATS are slightly higher because they prioritize deadlines or energy over immediate execution. Next, moving to the average turnaround time graph. This round robin performs slightly best here due to balanced execution, and EDF and EATS are slightly tighter, higher as they focus on meeting deadlines and reducing energy. Next, moving to the total energy consumption chart. This is a critical metric. Most algorithm consume similar energy. Here, round robin consumes slightly more energy due to frequent context switching. EATS maintain optimized energy usage, showing the benefit of energy-aware scheduling. Next, we have deadline success rate chart. This graph shows how well deadlines are met. As FCFS, SJF, RR performs better here in this case. EDF and EATS shows lower success, which indicates that under certain workloads, energy constraints or scheduling overhead can impact deadline performance. And in the last, we have CPU utilization shows how actively CPU is used over time. We can see peaks where workload is high. Here at time 11.4, the workload is high, 100% CPU utilization, and here at T is equals to 6, the utilization is just 50%. So, in conclusion, these charts demonstrate the trade-offs between performance, fairness, deadlines, and energy consumption. While traditional algorithms optimize speed or fairness, each combined with DVFS provides a more balanced real-world approach by optimizing both performance and energy efficiency.